Okay, so second part of our lesson for limits at infinity. Now we want to be able to do limits algebraically. So what is going to happen in here is I'm going to put in here algebraically. We're going to see different cases from easiest to most complicated. Let's start with functions that are friendly to us. Let's start with polynomials. So let's say that we're being given a polynomial. Let's say that the function that I'm working with is y is equal to negative 4x cubed plus 7x squared plus x minus 5. And we're being asked both what is the limit when x goes to positive infinity of this function y, and what is the limit when x goes to negative infinity of this same polynomial y. And this is pretty easy, you guys have done this before. The idea with the polynomial is that polynomials have a leading term. The leading term is the one with the highest exponent. It's called a leading term because it leads the behavior for positive or negative limits. What happens in here, the rest of the limits, the rest of the terms are sort of negligible compared to that one when you're working with really big values of x, either positive or negative. So what you have to do is picture what would happen if you plug in a really big positive number into negative 4x cubed. You will get a humongous negative quantity. So the limit is negative infinity. There is no limit. The interpretation of this is that as you plug in bigger and bigger positive numbers, x goes to positive infinity, the function gets smaller and smaller and smaller. You just found the end behavior is something like that. Whereas for this case, if you plug in very negative numbers into negative 4x cubed, raise a negative number to the third power, that's going to be negative, with a negative 4 is going to give you positive, you're going to get a humongous positive thing. So we say that the limit is positive infinity. Again, this means that there is no asymptote, no horizontal asymptote, but it tells you that when you go into this direction into your graph, when x goes to negative infinity, your outputs are going to positive infinity. Your graph is going up. This has implications with regards to end behavior for sketching the graph, and also for being able to find absolute extrema, absolute maximum, absolute minimum. You can see that this is very easy. But again, no horizontal asymptotes. For you to have a horizontal asymptote, the limit going to positive or negative infinity has to exist. Okay, the next case we want to look at is the limit going to infinity are reciprocal of powers. So what I mean is a situation where you're being given the limit when x goes to either positive or negative infinity of a constant divided by some kind of power of x, with r being a positive exponent. So for instance, this would be, let me give you a more concrete example. The limit when x goes again to the positive or negative infinity of 7 divided by x to the fourth power. And again, this is a matter of doing common sense. If, oh, my whole thing disappeared. X to the fourth power and 7. If x gets larger and larger and larger, when you raise that to the fourth power, you can see that this part in here is going to become really, really big. And it doesn't matter whether it's a positive big or a negative big, the denominator is going to get huge. If the numerator stays at 7, 7 divided by a really big quantity, so 7 divided by either positive or negative infinity, in this case positive infinity, is going to get closer and closer to 0. I'm not saying that this quantity will ever be equal to 0, I'm saying it will get closer and closer to 0. So these limits are very easy. They're always going to be equal to 0. Now, taking those two ideas together, I can do limits like this next one. Look, limit when x goes to, let's say, positive infinity. By the way, your book does not say positive, it says infinity, but that means positive. Or let's say 4 plus 1 over x to the fifth power. Now, what is the trick for this programming here? Well, the trick is that when I have addition or subtraction, I can look at each limit individually. So what I'm going to have in here is what happens with 4 when x gets really, really, really big. Well, nothing, 4 is a constant, so that part is just 4. And what happens with 1 over x to the fifth power when it gets really, really, really big? Well, this whole thing is going to get closer and closer to 0. So as a limit, the first term gets closer and closer to 4, the second part gets closer and closer to 0, so the whole limit is going to be equal to 4. Very easy. Okay, let's get now into limits going to infinity in which we have rational functions, so a fraction divided by a fraction. These are very important, these show up a lot. Let's say limit when x goes to infinity of 3x minus 1 over 5x squared minus 2. Okay, so what is the issue here? Well, the issue is that I can look at the limit of the numerator, the limit of the denominator, and think about what happens. The numerator by itself is a polynomial. The leading term is 3x. When x goes to infinity, the numerator is going to become bigger and bigger and bigger, something really big, positive if you want to. The denominator is also a polynomial. 5x squared is the leading term. When x gets really, really big, 5x squared is also going to get larger and larger and larger. And right now my limit is an infinity over infinity, which unfortunately for us, it's an indeterminate form. Indeterminate form. This is not the first indeterminate form that we see. This is related also to that dreaded 0 over 0 that we found for limits before. Indeterminate form means that something has to be done. That's not the answer for the limit, but that this approach did not work. I need to try something different. So what do I do to resolve this situation when I have a polynomial divided by a polynomial? So this is something that you probably saw last year in math analysis. The trick is look at the denominator, always the denominator, select the largest power of the denominator, just the power, so it's x squared, and multiply by the reciprocal of that largest power, so 1 over x squared, both numerator and denominator of the original limit. What am I talking about? Let me write it in here slowly. So the original problem was the limit when x goes to infinity of 3x minus 1 over 5x squared minus 2. Once I have decided that I have an indeterminate form, I'm going to multiply the numerator and the denominator by the reciprocal of the largest power, always of the denominator, in this case 1 over x squared. Then I'm going to distribute that to each of the terms that I have inside the parentheses. So I'm going to have the limit when x goes to infinity, and 3x times 1 over x squared is going to give me 3 over x, minus 1 times 1 over x squared is going to give me 1 over x squared. That's the numerator. In the denominator, 5x squared times 1 over x squared is going to give me a 5, and 2 times 1 over x squared is going to give me a 2 over x squared. And now what? Well, now I can use what we had seen before. Let me come back up here, that as long as you have a constant divided by a power of x, and you're going to positive or negative infinity, that's going to get closer and closer to 0. So in this part in here is a constant divided by a power of x. As x gets larger and larger and larger, that's going to get closer and closer to 0. So will this one will get closer and closer to 0. So your numerator gets closer and closer to 0 minus 0. In the meantime, the denominator, this part gets closer and closer to 0. The 5 doesn't change, so that gets closer and closer to 5 minus 0. So the overall limit is 0 divided by 5, or just 0. So the limit exists, and we can conclude that there is a horizontal asymptote to this graph with equation y equals 0, which is pretty cool. I didn't know that. One of the neat things about horizontal asymptotes and rational functions is that for rational functions, as long as you have a polynomial divided by a polynomial, the limit going to positive and negative infinity, if it exists, will be the same. So I can tell you right now that if we had done this limit again, going instead of to positive to negative infinity, I would also have got y equals 0. But again, that's also only true if the limit exists, and if we have a rational function, the same one going to the polynomial divided by a polynomial. Let's do one last example of a rational function, and then we'll move on to something else. Let's take the limit when x goes to infinity of, let's say, 4x cubed minus 7 or plus 7x, better. And then in here, let's have x squared plus 5. Okay, so your thinking for this problem should be, if you plug in something really, really big and you look at 4x cubed, that's going to end up giving you something humongous positive. Plug in something really, really big and you just look at x squared, the leading term, that's going to give you something really, really big positive. That's definitely going to give you an indeterminate case. Largest power of the denominator is x squared. Its reciprocal is 1 over x squared. I need to multiply top and bottom by 1 over x squared. To multiply top and bottom by 1 over x squared. Okay, so what am I going to get? I'm going to get the limit when x goes to infinity on the top. 4x cubed times 1 over x squared is 4x. 7x times 1 over x squared is 7 over x. On the bottom, x squared times 1 over x squared is 1. 5 times 1 over x squared is 5 over x squared. Now I do my thinking, what happens when x gets really, really big? Well, this 4x gets huge positive, so I have something really humongous positive. This 4 over x is going to get closer and closer to 0, so plus 0. This 1 stays, doesn't do anything, so 1. And this 5 over x squared is going to get smaller and smaller, getting closer and closer to 0. So my numerator is getting humongous, my denominator is getting closer and closer to 1. What is this limit going to be equal to? This limit is going to be equal to positive infinity. And that means that there is no limit and no horizontal asymptote for this problem. We also have an issue, since there is no horizontal asymptote, I'm not guaranteed that the limit going to negative infinity would also be positive infinity. I would have to analyze that one. So this issue that you will have the same limit going to positive and negative infinity for rational functions only happens if you have a limit, if the limit exists. If it doesn't exist, you would have to look at each of them differently. Now, again, the implication visually is that this function that I have in here, when x goes towards positive infinity, the function itself goes to positive infinity too. So the graph is doing something like that. That's going to help me later on sketching it. And this concludes this situation with rational functions. I just have one more case to show you in another video.